Okay, this is from chapter 23, problem 3, which says rearrange the equation current equals voltage over resistance to express resistance in terms of current and voltage. Then solve the following. A certain device in a 120 volt circuit has a current rating of 20 amps. What is the resistance of the device? How many ohms? So the original equation is current I equals voltage V divided by resistance R. So to solve for resistance R means that I get the R to the other side, so I multiply with it, and at the same time I divide by I, which means I have voltage divided by current. There's a third equation that they don't ask for, but I do it anyway, which is that to solve for the voltage V, which means that I multiply with I, so it's R times I. Notice the other equation, of course, gives the same thing. Voltage equals I times R as I get it to the other side. So V equals R times I. And for these here, there are certain representations. One of them is circular, and another one is triangular. I'm just going to do the circle here. There we go. And let's see if I see a line that I can use here. Maybe this one. And there we go. And make it black, I guess. There. Alright, there's one. And there's one. And put V on the top. And R and I at the bottom. It doesn't matter if it says R and I or if it says I and R, as long as the V is on top. And what this means here is that V equals R times I. V equals R times I. Or R equals V over I. R equals V over I. Or I equals V over R. I equals V over R. Okay, so that way it can be memorized as well if you memorize this circle or triangular representation. As I said, you can look up triangle, looks exactly the same, except it's a triangle. Anyway, it says that a certain device in a 120 volt circuit has a current rating of 20 amps, so I have V equals 120 volts and I equals 20 amps. What is the resistance? So for that one, since I'm supposed to figure out the resistance, I should use this particular equation. So R equals V over I, which is 120 volts divided by 20 amps, which is 6, of course, and volts divided by amps, that's what the unit would be, but that would be expressed for the standard units for resistance, which is ohms. And of course this is handwriting. Actually, that's kind of pretty handwriting. In the book you may see something like that, but you know, if I don't get that quite right, sometimes I'm a little sloppy. I do this here. Either one of them is supposed to mean ohms, just like this one here is supposed to be an R and this one here is supposed to be an I, and as long as it's legible, nobody is going to complain about it. So as long as we can read my handwritten ohm as an actual ohm, then nobody should complain about it. This problem is from chapter 23, number 4. It says, using the formula power equals currents times voltage, find the current drawn by a 1200 watt toaster connected to 120 volts. Then using the method from the previous problem, show that the resistance of the toaster is 12 ohms. So it says power equals current times voltage. There we go. All capital letters. Find the current drawn by 1200 watt toaster. So the toaster produces a power of 1200 watts, and it's hooked up to an outlet with a voltage of 120 volts. And with that, we're supposed to figure out what the electrical current is. And of course, this one here, as far as the algebra goes, would be that electrical current equals power on the other side divided by the voltage. So divide by voltage. So 1200 watts divided by 120 volts, which of course is 10, and then the unit is watts divided by volts, because we're supposed to come up with electric current in standard units. These are standard units, so we're going to come up with standard units as well, which is amps. So the answer is 10 amps. Then, using the method from the previous problem, show that the resistance of the toaster is 12 ohms. So with that, we're supposed to figure out what the resistance is, and resistance is voltage divided by electric current. So that's 120 volts divided by 10 amps. That of course is 12, and volts over amps would be the units. Again, this is standard units, so for resistance the standard units has to come up, and that is 12 ohms. And as I mentioned before, this is my way of writing it in handwriting, and as long as it's legible and comparable to the way it's printed, then that should be okay. This problem is from chapter 23, number 5, automobile and battery. It says the total charge that an automobile battery can supply without being recharged is given in terms of ampere hours. A typical 12-volt battery has a rating of 60 ampere hours, 60 amps for 1 hour, 30 amps for 2 hours, and so on. Suppose that you forget to turn the headlights off in your parked automobile. If each of the two headlights draws 3 amps, how long will it be before your battery is dead? Okay, first of all, we have to decide here what kind of circuit do we have. Do we have a series circuit, or do we have a parallel circuit? So I forgot. Okay, so here let's draw a series circuit. Takes a little bit. And this was supposed to be my battery right here. And then I'm going to draw a lamp in here and a lamp in there and fix the connections here a little bit. Okay, well, what if one of them actually goes out, like this one here? Well, in that case, I actually have a gap in there, pretty good gap, and I have no electric circuit anymore, closed electric circuit anymore, and the second headlight over here will also go off. So by default, the circuit for the two headlights would have to be in parallel. Here is the battery, and here are the two headlights. There's one, and there's one, and here's a connection. There we go. So I have a closed circuit here, two headlights in parallel, and if one of them goes out, such as this one, then for the other one, the circuit is still closed and it will keep shining. And that, of course, is the way our car headlights are operating, that if one goes out, we still have the other one available. And if we drive at night and continue doing that, sooner or later we will be pulled over. Anyway, I checked out circuits on the internet to come up with an example, and here is one. And here's the positive, that's from the battery, and that's indicated by a red wire. Notice there's nothing on the negative, but that's because it's connected to ground, just as all the other appliances here, such as the headlights or the high beam indicator or the dimmer over here, in the schematic the negative actually should be connected to ground as well. Anyway, there's a wire going here through what is called a starter solenoid. That means this one here has to get started first for any of the headlights to be turned on. So that means that for in this kind of schematic, if your car is actually not running, the headlights are not going to turn on. So you're actually safe against what the problem actually says. But in some older cars, and some are still manufactured, you could actually accidentally leave the headlights on. In any case, here goes the current, and then it goes in here and in here. Now, of course, it has to be connected. Well, that's where the dimmer comes in. So I guess this is the low beam, and then this here is the high beam. So let's look at the, I'm sorry, this one here. This one here is the low beam, and this one is the high beam. That's just where the current comes in. And this is the headlight switch, which then tells the dimmer which mode to be in. And let's just look at the low beam, where then the current from the other direction flows this way here and going in there, and then this one here is connected to that one over there, and current is flowing in there and going back to the ground. And over here for the other one, current is flowing in here into the headlamp and to the ground. And the dimmer here, this one here, basically tells the relay to do this here, or the other one, the high beam, tells the other relay to do this here and connect and make it a high beam. But notice that if something here is broken on one of the headlights, then the other one is still functioning because the current can run through the headlight. I found another one which is really pretty, I would say. This tells you the entire electronics and electrical wiring inside a car. We can obviously see the headlights here. Here's the battery. All these little orange things here, they mean grounded. That's what I said earlier about the negative of the battery. And then if we followed here from the headlamps all the way around here, I didn't get into detail. When I looked at this one here, we could figure out that they're indeed wired in parallel. Okay. Anyway, that was a long story to figure out that our headlights need to be in parallel, which means, yeah, this one here is not going to work. Okay, now it says in the problem that we have a typical 12-volt battery, so V equals 12 volts, and that the battery has a rating of 60 ampere hours. So at most, this is how it can use up. By the way, the unit for that would be in coulombs, pretty large, so it would be actually a charge. So the charge of the entire charge of the battery would be this one here, expressed in amp hours. Makes it a little bit easier for the calculation than coulombs itself. And then it says, suppose that you forget to turn the headlights off. If each of the two headlights draws 3 amps, how long will it be before your battery is dead? So for each of them, we have 3 amps going through here. 3 amps going through here. And of course, with the junction rule, oh, notice that I drew this in the opposite way. Whoops. Didn't pay attention here. Because my positive terminal is over here, the current should go in this way. There we go. As far as the problem is concerned, that's no biggie. What a little mistake that I just made, but I want to do it proper anyway. Okay, so 3 amps going through each one. According to Kirchhoff's rule, with this one here being a junction, the current that splits up right here and then comes back together at the other junction is the total current of the entire circuit. So I have 3 amps flowing through here and 3 amps flowing for this one, which means that the total amount of current that goes in here must be 6 amps. And of course, as written earlier on, the battery itself is 12 volts. Okay, at this point there's actually a quick way of doing this, and that is to say, okay, I know what the rating is, 60 amp hours, and I know what the current is 6 amps, and if I put these two together, amps and amps, they may divide, and I'm left with hours, and that's exactly what they're asking for. How long will it be before your battery is dead? So I'm just going to put this together here without actually drawing on any one equation from the book, but this should make sense. And then I would have charge divided by current, 60 amp hours divided by 6 amps, which is 10. The amps divide, and I'm left with hours, which means that charge divided by current is time, and the answer is that it takes 10 hours for the battery to drain. As I said, this one is the quick way. Here is the proper way, and for that I would, as I said, this one here is, oops, I'm sorry, this equation here I just came up with because it made sense, but there is a proper way of doing it with looking at equations that we have encountered before. One of them would be the amount of work that any kind of appliance can do, which is work is power times time. That is from quite a chapter, quite a few chapters ago. And then power is, as we encountered in this or the previous chapter, is electric current times voltage, and that is power times the time that is already over here. And then plug in the numbers. Well, actually, hold on. Before I plug in the numbers, let me just turn a couple of things around, which is volts times current times time. And notice that this last one here is amps times hours, which is given for the battery as 60 amp hours. And of course the voltage of the battery is 12 volts. And then 12 times 60 is 720. Which kind of unit? Well, this one is going to be volt amp hours. However, I should convert that to volt amp second. And in volt amp second, that would be the basic unit for work, standard unit, which means that is actually the joules. So I'm going to take this number here and convert it hours to seconds, which is times 3,600, which is 2,600,000 joules, or 2.6 million megajoules. And now I'm going to say, well, what's the time then it will use to drain at 6 amps? Well, I'm going to do time using this equation here, and of course that is work, the amount of work that the battery could deliver divided by the current and the voltage, and that would be then 2,600,000 joules divided by the current of 6 amps and the voltage of 12 volts. And when I calculate that out, I come up with 36,000 seconds. By the way, my 2,600,000 joules earlier was a rounded number, so the 36,000 here again is rounded. And that one then is 10 hours because there are 3,600 seconds in the hours. Of course, that's the result I had earlier. Notice that my second calculation is a whole lot longer than the first, but I did that in order to show the proper way and the shortcut that I just discovered by looking at the numbers. So either way of them, either one of these two works. This problem is from chapter 23, number 10. It says, in periods of peak demand, power companies lower their voltage. This saves them power and saves you money. To see the effect, consider a 1200 watt coffee maker that draws 10 amps when connected to 120 volts. Suppose the voltage is lowered by 10% to 108 volts. By how much does the current decrease? By how much does the power decrease? Caution, the 1200 watt label is valid only when 120 volt is applied. When the voltage is lowered, it is the resistance of the toaster, not its power, that remains constant. I will mention something later to that effect. In any case, so what we have going here for the coffee maker is that the 1200, that's rated at 1200 watts, only if the voltage is 120 volts. But now that voltage is lowered by 10% to 108 volts. So 10% decrease here. That's what they say. Okay, by how much does the current decrease? Well, for that I have to do this calculation. First of all, figure out what the current is, the original current. P equals I times voltage, which means that the original current is power divided by volts, which is 1200, watts divided by 120 volts, and I'm going to write down here the original current. There we go. Which is 10 amps. That makes sense because 10 amps times 120 volts are 10 amps times 120 volts are 1200 watts. Okay, now what I could do is just take the 10 amps and multiply by 108 volts and come up with something. However, I'm just telling you that's not correct. Let's do something else instead, and that is determine what the resistance is of the coffee maker. And that's what it says here. It's the resistance of the toaster. Ooh, interesting. They say coffee maker first and then they switch that to toaster. Oh well. It's the resistance of the toaster. It stays constant. So let's calculate the resistance. R equals 120 volts divided by 10 amps. So, oops, you know what? Start over again. Because I meant to write down here proper form of resistance, volts divided by current. So I have 120 volts divided by 10 amps, which means that our coffee maker or toaster, whatever it is, has a resistance of 10 ohms. I repeated that because I had forgotten this one here, and then I wrote down the wrong unit there accidentally. Okay, in any case, now it says that the resistance of the toaster or coffee maker is the same at 10 ohms even at the new voltage. So let's calculate for the new voltage, and something interesting will happen here as we calculate the electric current for this one here. Electric current with Ohm's law is going to be voltage divided by resistance. So the new voltage is at 108 volts. The resistance is still 10 ohms. That's what they say in the problem is the same. Any appliance or electrical part where you don't change its makeup will keep the same resistance, 10 ohms in this case, and I come up with 10.8 amps. And notice that that is different, and it doesn't look right the way I calculated it does. Oh, geesh. I hope you noticed that mistake earlier. Oops. That might be the very first time ever that I can correct one mistake, because maybe I didn't make a mistake earlier. Anyway, 120 divided by 10, that's not 10 ohms. Sorry about that. That of course is 12 ohms. There we go. Which means that down here I have 12 ohms. I distracted myself because my computer is doing something else. And so my eye keeps looking to the upper left corner outside of the screen here, and I distracted myself. Anyway, and then 108 volts divided by 12 ohms indeed is, if I find my calculator here, a little over 8 amps. 9 amps. 9 amps, which is definitely not the same as this one here, which is also 10% lower, and that's what they're saying, 10%. By how much did the current decrease? Well, it also decreased by those 10% down to 9 amps. And that makes sense because for the same resistance of 12 ohms, going to a lower voltage means that we have to get to a lower current as well. Okay, let's see what the power is. So the new power is current times voltage, which is the just calculated 9 amps times 108 volts, and that one comes out to 972 amp volts, which of course is watts. So the total power has decreased appreciably from 1200 to 972 watts, approximately by 20%. Not exactly, but that's because as you subtract 10% twice, and this is what happens here, you subtract 10% here, you subtract 10% here. So as you subtract 10% twice, what you actually do is you multiply by 0.9 instead, twice, and therefore you come up with 972 watts as the power for the coffee maker or the toaster, which means if you get less voltage from an outlet, your appliance isn't going to work as well as it should, which may be okay, just leave the toaster on for a longer time. But if you went the opposite direction, that could actually cause a hazard or be a hazard, because now you would actually draw more power than the appliance allows, and then it may fry itself. So as you go to the higher voltage, pay a little bit of attention, especially if you go to another country where they may have a voltage from the outlet of 240 volts and where then should use a transformer. This problem is from chapter 23, number 11, a simple circuit. And it says, for a circuit of one light bulb of resistance 4 ohms and a voltage source that provides 6 volts, compute the power output. And then part B is, for a circuit of one resistor with resistance 50 ohms and a voltage source that provides 100 volts, compute the power output. Okay, so here's the first circuit, part A. Got a light bulb here. And let's see, I'm going to have a power source here, and then I'm going to do the wiring. There we go. And if I hadn't made a gap there a moment ago, I would actually have a closed circuit. There we go. All right. So in order to figure out what the power output is, power equals current times voltage. I would need to know what the current is. I know what the voltage is, given as 6 volts. So I need to know what the current is. Well, the current I get from Ohm's law in the form of the current equals voltage divided by resistance, which then is given as 6 volts divided by 4 ohms, and that is 1.5 amps. And then I plug that in here. Power equals current times voltage, so 1.5 amps times 6 volts, and that comes out to 9 watts. Okay, the second part is virtually the same. The calculations are really virtually the same. I'm going to see if I can just copy everything here and carefully pull it down without losing anything, and then just fix a few things, such as this will be her problem B, and I have different numbers here on the second part. And of course, in this case, I do have a resistor. I'm going to take this out here. And we'll draw in the resistor. And there's the wire. And then I will write on here 100 volts. And this one here is 50 ohms, which actually in the last problem I had forgotten to write on. Always makes it look a little better and more complete when we write those designations on there. Any case, same calculations here. Current equals voltage divided by resistance, so 100 volts divided by 50 ohms equals 2 amps or 2.0 amps. In these kinds of problems, we assume that these are exact numbers, that really 100 volts is applied to an exact 50 ohm resistor, each one of them with just a small error. So that's why I go out to significant figures here. Should have done that over here too. That should be 9.0 watts. Okay, and then so I have 2.0 amps here, and I multiply that with 100 volts, and that equals 200 amps. Oops, 200 watts. Okay. There are a couple of follow-up problems that will be more complicated. The first follow-up problem will be a series circuit with several elements, several side light bulbs or resistors, and then the next problem will be a parallel circuit, also with several light bulbs, respectively several resistors. So we be calculating more along the same lines, making it a little bit more complicated. But before I go there, I figured I'm gonna actually show you a simulation applet. So here we go. This one here is from PhET, P-H-E-T, Physics Education Technology. And I'm gonna grab a light bulb, and if I remember correctly, that light bulb has a resistance of 4 ohms. So there we go. Show value 4 ohms. I'll put a wire on this one here. I'll put another wire over here. And might as well use a switch. Could have used that on the other one too. Apparently I have to pull on the joints. I'm going to put an ammeter in here. And I need another wire to connect. There we go. And yet another wire there. And I need a battery. There we go. And it's at 6 volts on the first one. So 6 volts. Show the value. There we go. It says something about internal resistance. For our calculations, it would be good if we just had 0.0 ohms internal resistance, but I'm going to put 0.01. Oops, that was interesting. I will put 0.1 ohms because it's more realistic. The battery itself is actually also drawing a current and using up power. That's why when you short circuit a battery, the battery will heat up because it's using up its own power. Okay, the circuit is closed, except I still have to close the switch. And here, keep in mind how bright they make this light bulb here as we go later to the parallel and series circuits. So keep in mind how bright this one actually is. I don't think I can move everything at once. No, I really can't. Look at the current here, 1.46 amps. It's not exactly 1.5 amps as calculated, but that's only because I put a little internal resistance in here. So this one here is actually around at 1.5 amps, which is the same thing as the problem was. Again, if I change the internal resistance here on the battery itself, I do come up with exactly 1.50 amps. But this one here is more realistic. Okay, and then of course 1.46 or 1.5 amps rounded times the 6 volts on the battery, that comes out to the calculated 9 watts. Okay, now the resistor. So I'm going to put a resistor in here. There we go. Okay, and it says in there that it's a 50 ohm resistor. And the battery is now supposed to be 100 volts. That's quite a battery. And close the, oh yeah, show the value here. There we go, 50 ohms, close it. And I come up with 2.00 amps, even though the battery has some internal resistance. It's so small compared to this 50 ohm resistor that it really doesn't affect the current. So it's really the resistor that is using up the power. And so, just as calculated before, 100 volts divided by 50 ohms is 2 amps. And then 2 amps times 100 volts is the 200 watts that are being used by the resistor. In this case here for this applet, it doesn't show the calculation for the power, so we still have to do it, but that's really easy. 2 amps total current times 100 volts for the power, which makes 200 watts. This is a problem from chapter 23, number 12, series circuit. It says for a series circuit of A3 identical light bulbs, each of resistance 4 ohms, and a voltage source that provides 6 volts, compute the total resistance and the total power output. Then, for a series circuit of B3 different resistors with resistances 50 ohms, 30 ohms, and 20 ohms, and a voltage source that provides 100 volts, compute the total resistance and the total power output, and then in the process derive the formula for adding resistances in series and Kirchhoff's loop rule. Now, as far as adding resistors in series or in the next problem in parallel, our book isn't really doing that, but I decide that it is important to do it, so I made up these problems, and you will have to become familiar with the formulas for adding resistances in series, which is simply adding the resistances, and adding resistances in parallel, which you will see is adding the reciprocals, but that'll be the next problem. Okay, so for this one here, it would be a circuit that looks like this. This would be part A. So there we go. 3 identical light bulbs. Oops. And actually I noticed that on the last one I put, on the applet, I put an ammeter there, so I'm going to put that here too, except that wasn't drawn very nicely, so there we go. And here's the battery, and it says 6 volts, and then it says 4 ohms, 4 ohms, and 4 ohms, and again, that's just my handwriting here. That 4 didn't look very nice. 4 ohms there. Okay, And now it says compute the total resistance and the total output, total power output. Well, I figured let's go to the circuit over here first, to the one that we can build, and do it right here. Take this resistor out and put the light bulb back in, except I need more light bulbs and a little bit more space. Yep, that's fine, but I also need to change the resistance here. That was 4 ohms. I actually do need even more space. Okay, that would be actually moving it out of the picture. There we go. I'll tell you later why I need more space. Okay. 4 ohms, and again I want to show the value, show the value, show the value. I actually decided to kick down the battery's internal resistance to 0.0 ohms because otherwise I would have to round numbers left and right, and I think that would make it more confusing. So I'm just going to leave it as 0.0 ohms, so there won't be any rounding involved. Actually, let me move that resistor out of the way here. Alright, I need 2 more wires. Oops, careful. There we go. And there we go. Okay, and then I close the... Oh, that is bright. Okay, I forgot something. There was the old circuit for the resistors at 100 volts. So I just want to have it at 6 volts here. And now much fainter. I actually compared this one to the circuit we had earlier with just a simple circuit, and notice that each of the light bulbs is actually fainter when they're all in series. We can simulate just the one light bulb again. I think all I have to do is just take 2 light bulbs out of here and notice what happens now. Okay, relatively bright, this one light bulb here, but notice if I put all 3 of them in series, then they're quite a bit fainter. Okay, so what we get here is a total current of 0.5 amps, and we have a total voltage of 6 volts, and so we're going to get a total power of 3 watts, 0.5 times 6, so 3 watts. That was one of the questions that was listed in there. Let's see, the other question was, compute the total resistance and the total power output. So we're actually halfway down here. Let's see the total resistance. I'm going to turn this off here for just a moment. So each of these here has 4 ohms, and I come up with 6 volts and 0.5 amps, as we saw a moment ago. Well, if I use Ohm's law, then I would say 6 volts divided by 0.5 amps, which is 12 ohms, is the total resistance. And that actually answers a follow-up question which says that what's the formula for adding resistances in series? Well, 6 volts divided by 0.5 amps is 12 ohms, and when I look at the individual resistances, 4 and 4 and 4 is of course 12 ohms as well. So that pretty much answers all the questions that are listed there, but let's do it on paper anyway. Okay, oh, this is the FET team here, I guess, some of them. Physics, Education Technologies, but I meant to go there. There we go. Alright, so 3 at angle each in a voltage source, compute the total resistance and total power output. Okay. Actually, I will turn to the book here, which says on series circuits, among other things, that electric current has only a single pathway through the circuit. This means that the current passing through the resistance of each electrical device along the pathway is the same. That means the 0.5 amps that we saw is running through any one of those resistors. I will go back in a little while and show you that in the simulation. And then it also says that the voltage drop across each device is proportional to its resistance. Ohm's law applies separately to each device, and so that means that the voltage drop on each one of these here is the same and equivalent to each resistance. That's also why it shows equal resistances across here, so each one of them is 4 ohms. There are 3 of them, so they have to share the voltage, so each one of them gets 2 volts of that voltage drop of 2 volts. And then the current that flows through here, well, I calculate that in just a moment. For each one of these here, Ohm's law applies separately, so it's current equals voltage divided by resistance, which is 2 volts divided by 4 ohms, which is 0.5 amps. And of course they're all the same here, so my calculation goes for any one of them. And then it says in here the current is the same running through all of them, so through each of these here it's 0.5 amps running through here. Okay, then the total power is the current times the voltage. Well, the total current is 0.5 amps. The total voltage is 6 volts. Again, it's 2, 2, and 2. And that one then comes out to 3 amp volts or 3 watts. Okay, it says here, in the process derive the formula for adding resistances. Well, if we look at this one here, Ohm's law again, for the total, these here are for the individual ones. So this one here was for the individual ones, but now it's going to be the total. So total equals total voltage divided by the what is called the equivalent resistance. I need to push this over a little bit. Well, I have 6 volts, of course, as the total. And I divide that by the equivalent resistance, which is 12 ohms, 4 plus 4 plus 4. And that is indeed the total current of 0.5 amps. Okay, now here the 12 ohms, where did I get that from? Well, the equivalent resistance in series is add the resistances just the way they are, which is 4 ohms plus 4 ohms plus 4 ohms. And that is a total of 12 ohms. Okay, let me just go back to the simulation. And it said something in the book of that the current is the same going through each one of them. So let me show you that. It's 0.5 amps is the total current. And I need to split the junctions here. And there are 2. And then I put the piece of wire there. And I put this one in here, hopefully. Oh, I have to shift this down a little bit. There we go. Didn't quite do it. Maybe. I think now it did it. Okay. Alright, 0.5 amps going through this lamp here, and you probably can believe that that would be the same thing over here. As far as the voltage on each of these concerned, I just introduced a voltmeter, and I'm going to hook it up here, and it reads 2 volts on this light bulb, and it reads, no, not 4 volts, that's the 2 light bulbs together, but 2 volts on this light bulb, and then it reads 2 volts on this light bulb. So indeed they're splitting up the voltages proportionally. Okay, so here let's go to the second part of the problem. We have a series circuit that for 3 resistors that looks as follows. So 3 resistors. Again, I will put an ammeter in there, and again that was a sorry excuse for an ammeter drawing. There we go, and now it says that we have a voltage of 100 volts and we have 3 resistors of 50 ohms, of 30 ohms, and of 20 ohms. There's also a reason why I chose these numbers, why I chose this one to be 100 volts and why I chose these 3 resistors to add up to 100 ohms. And you will see that as we go to the simulation. Okay, first of all I'm going to unhook the voltmeter and actually take it out of the way. And I will see if I can remove that light bulb. Oh, notice? As soon as I removed one, nothing works anymore. As soon as I reconnect it, there we go. So in a series circuit, if you remove one of the components, or if it breaks down one of the components, then the others are not working. That, of course, is what the book is telling us as well. Okay, so I'm going to take this one out here, and I'm going to take this one out. I didn't mean to connect that. Okay, it keeps connecting these junctions here. It keeps doing that. I cannot move it away. Just let me move it away. Oh man. There we go. Alright. So I put a resistor in here. Oh yeah, the first one is actually 50 ohms. And the next one is going to be 30. Show the value. And the third one is going to be 20. Show the value, and then I put this one in here, and then it's already working, except I have to change the voltage because it says 100 volts. Alright, and we already see the result here, one of the results. The current is 1 amp, and that also means that the power being consumed is 100 watts. 1 amp times 100 volts, which is 100 watts, and just show the value here. Okay. Again, for a series circuit, it says the voltage drop across each device is proportional to its resistance. Ohm's law applies separate to each device, and that's why it shows them as 50, 30, and 20, and this one as 100 here, because we can see here that the 100 volts will be nicely split up into 50 volts, 30 volts, and 20 volts, because that's exactly what that sentence says. So I'm going to use a voltmeter, and I show that right here we got 50 volts. Then over here we got oops, there's the junction, 30 volts. And then over here we got 20 volts. Okay. I'm going to take the voltmeter away. What do I want to say? The current being measured is going to be the same everywhere. So a moment ago we measured 1 amp, so I'm going to put the current meter in a different place, and it says 1 amps. And if I yet put it somewhere else, I have to be fast doing this here, because otherwise these junctions there connecting themselves kind of more or less automatically. It's kind of nice that they do that, but sometimes I just do it too fast. And so when I put it down here, I again have 1 amps. I'm sorry, 1 amp. So the current is flowing the same everywhere. Okay, let's go back to this one here. So what I just showed is what the book is saying, that here we have 50 volts on this resistor, 30 volts on this one, 20 volts on this one, and again individually the current is, for example, 20 ohms, 20 volts divided by 20 ohms, and that of course is 1 amp. So again, this was the individual one. Which goes to this one here. And then of course it would be also 30 volts divided by 30 ohms, 50 volts divided by 50 ohms. And a total current of 1 amp applies to all of them. Electric current has only a single pathway through the circuit. This means that the current passing through the resistance of each electrical device along the pathway is the same, in this case 1 amp. And that means that the total current is that the total power is 1 amp times 100 volts, which is 100 watts. Okay, so 100 watts is what the total power is. And you may recall from the previous problem that for just a 50 ohm resistor, we actually had 200 watts. Okay, and for the light bulbs here, we calculated 3 watts for 3 identical light bulbs, and these 3 identical light bulbs, they actually have to share those 3 watts, which means each of them just gets 1 watt. You can again see that by calculating 2 volts times the individual, or the total 0.5 amps. So each one of them gets 1 watt, compared to the single light bulb that gets actually 9 watts. Same light bulb, same voltage, just one light bulb gets 9 watts. Here, these 3 you have to share the 3 watts right here, which means each one of them gets 1. And that's what we saw in the simulation earlier, that with these 3 light bulbs in series, they're a whole lot fainter than if you just have one of them in there. Okay, what is the total resistance? Well, again, they're going to add up as equivalent resistance equals the first resistance plus the second plus the third. So this is the really important information that may not be in the book, but that I do want you to be aware of and do calculations with it. So in this case here, it's 50 ohms plus 30 plus 20, and that comes out to a total of 100 ohms. And again, if we look at Ohm's law for the total, then we would have the total current equals 100 volts divided by 100 ohms as the total resistance, and that of course comes out to 1 amps. Okay, one more little thing, and that is Kirchhoff's loop rule, which says that when we add the voltages around here, we come up with the zero voltage that we have on this side. The book says the supply voltage is equal to the sum of the individual voltage drops across each device. And so as we go up here 6 volts inside the battery, then we have voltage drops of 2 volts, 2 volts, 2 volts, which of course add up to 6 volts. Or if we go around once, it would be 6 volts up, and then 2 down, 2 down, 2 down, which returns to the 0 over here. Same thing here, 100 volts of course equals 50 plus 30 plus 20. Or inside the battery we go up 100 volts, and then we subtract 50, 30, 20, and come back to 0 volts on the minus or ground side of the battery. So this is problem chapter 23, number 13 on parallel circuits. Again, this one is not in the book, and I added it because I figure it's important to know about parallel circuits and how resistances add in a parallel circuit, and you will see later that they add as reciprocals. Anyway, let's look at the problem here. So it says, for a parallel circuit of three identical light bulbs, each of resistance 4 ohms, and a voltage source that provides 6 volts, compute the total resistance and the total power output. And I'll be looking at the other parts later on. So here's the parallel circuit for the 3 light bulbs. Okay, I'll take the last one away again. A little bit too close. I think I will need a little bit of space to draw. Okay, and I think the rest I can do by hand. And I guess at some point I decided I wanted to put an ammeter in there as well, so I'll do that. Okay, so this one here is 6 volts. This one is 4 ohms, 4 ohms, and 4 ohms. And the book says, each device connects to the same 2 points A and B of the circuit. The voltage is therefore the same across each device. So imagine that we actually would not have these 2 here, but just 1 light bulb. That means across this light bulb we have 6 volts. However, what it is saying is that we have 6 volts across any one of these here, because they're all connected to the same point here. So here is 6 volts, here 6 volts, and here 6 volts, and on the other side it's all 0 volts. So the voltage drop in each one of them is 6 volts. There we go. Then it's saying the current divides among the parallel branches. Ohm's law applies separately to each branch. At this point we actually don't know what the current is, but we can calculate it in just a moment. What we do know is that the current divides among the parallel branches. So that means that a current is flowing in here. So as the total current is flowing through here, part of it will go this way, part of it will go this way, part of it will go this way, and all three of these here are added up to be the total current, which is what the next thing says. The total current in the circuit equals the sum of the currents in its parallel branches. The sum equals the current in the battery or other voltage source. It also said in here, I read that a moment ago, Ohm's law applies separately to each branch, and that's how we can determine the individual currents. So I equals V over R, which is individual currents. Remember, 6 volts divided by 4 ohms, so this is just as I used to do before, just this one here applied to just one of them. And that, of course, comes out to 1.5 amps. That means that here 1.5 amps is flowing through this light bulb, 1.5 amps through this, 1.5 amps through this. Incidentally, that was the same current that was flowing through that just simple circuit from a couple of problems ago, and that means that at some point we're going to expect that each of those light bulbs in the parallel circuit has the same brightness as the single one from the simple circuit. Okay, so anyway, so through each one of these here, it's 1.5 amps flowing through. So that means that the total current needs to be added up as the current flowing through the first and the second and the third, which is 1.5 plus 1.5 plus 1.5 in this case. Getting a little off the screen, I guess. And that equals, of course, 4.5 amps. Again, that's what it says. The current divides among the parallel branches. The total current in the circuit equals the sum of the currents in its parallel branches. And that, by the way, is Kirchhoff's junction rule, that the current flowing into a junction, which is this one here, this whole thing here is one junction, is the same as the currents flowing out of the junction. And then actually these three currents are coming back together, flowing, and 1.5 amps at each one coming back together, making a total of 4.5 amps. So the total is 4.5 amps, and actually with that one we can determine right away what the total power is. The power is, of course, current times voltage. The total current is 4.5 amps, and the voltage is given as 6 volts, so the total power is 27 watts. At the same time, we can also determine what the total or equivalent resistance is, okay, which is the total voltage, 6 volts, divided by the total current, 4.5 amps. And you'll be a little surprised because the total resistance comes out to 1.33 repeating ohms. So I'm just going to write down 1.33 ohms so we can see it at least, which is a little surprising because you look at 4, 4, and 4, and how could we possibly come up with 1.33 out of those 4s? Well, one of the things it says here, I haven't read this yet, is as the number of parallel branches is increased, the overall resistance of the circuit is decreased, and that's what we've seen. So we have 4 ohms, and we add 4 ohms and another 4 ohms, and the total resistance is supposed to decrease below 4 ohms, of course. Apparently it is 1.33 right now. Overall resistance lowered with each added path between any 2 points of the circuit. This means the overall resistance of the circuit is less than the resistance of any of the branches, and that's true. Okay, actually, if you look at the 1.33 ohms, it pretty much looks like 4 ohms divided by the number of branches, which is 3. 4 divided by 3 is 1.33. Repeating, I'm not going to write it down as such. This one happens to be a special case for a parallel circuit. Usually resistors, or in this case lamps that have a resistance, are not the same. So the actual formula will look somewhat different than just dividing 4 by 3. But we have answered quite a bit here in this particular part of the problem, and I'll do the resistors later, but let's go to a simulation. And that one is from the last one. I think I'm just gonna see if start this over. There we go. Okay, there's a light bulb, and again it's 4 ohms. Show the value, get another couple. 4 ohms, show the value, need a battery, and 6 volts for these. I don't think I can turn these here, and alright, I need an ammeter, and I need a bunch of wires. So there's one. Now the first one is gonna go there, and the next one is gonna go here. And I actually already have a closed circuit with the other two being not connected. Actually, that one is my simple circuit. Notice how bright it is. Now I'm going to connect these here. There we go. And there we go. And notice that the brightness actually stayed the same on these. And if I disconnect one of them, like one of them wouldn't work, well, then the other one is still going to work. And that's the nice thing about a parallel circuit. Let me, for example, take this one away. Okay, now, of course, I split the main circuit. So I'll try this again here. Uh-oh. Okay, if I could just move this here carefully away. Just, there we go. Okay, again, it's, there we go. There we go. Now I took this one out of the circuit, but the other one is still working as long as this is connected. So yeah, if I make a cut here in the main circuit, yeah, it wouldn't work. None of them would work. But if I just take one of them out, then the others are still working. Okay, and the third one. There we go. There we go. And they are all of equal brightness. And again, if I just took one of them out, wouldn't matter which one. Carefully move it over there. There we go. I took this one out. The other two are still working in parallel, just equally bright as they had been just a single bulb in a simple circuit. Okay, at this point here, all three of them are in parallel. What we can see here is the 4.5 amps that was calculated times the 6 volts on this one here is, of course, 27 watts. And then if we, for example, measure the voltage on any one of the 3 lamps, so here we go, 6 volts, 6 volts, alright, 5.99, and 6 volts, or 5.99 rounded to 6 volts. If we determine the current, that may be a little bit tricky. So I'm going to use another ammeter. we go. And there we go. We can see that it measures, or it'd say that 1.5 amps going to one of the light bulbs, and it would measure the same to the first and the third light bulb. The way I have it wired here, it makes it actually a little bit difficult to measure each individual ones. Oops. That's interesting. Why does it say 3 down here? Ooh, that should be still 4.5. Okay, the simulation for the most part works fine, but here it showed me something strange. That's probably the way I rigged it up, that it doesn't look like it's perfect. Let me actually... I need to fix this here, the way I show it, because otherwise... this may not... You could always claim that, hey, you know, something weird is going on here. So... definitely have to do it. There we go. Here. And you saw these other wires going in there earlier anyway. And then I need to split the junction here and split the junction there and take this out of the way. And move this down here maybe. And here. There we go. Put the next one in. Okay, at this point, yeah, this one actually will work. Whoa, I didn't know I could turn that. There we go, and there we go. There's the 1 point. Huh. Why is it doing that? Why is it still showing that? Oh, yeah, because I only have 2 lamps rigged up at this point. That's right. That's right. Maybe that's what happened earlier too. Okay, so here we go. 1.5, 4.5, which splits up into 3, 4.5. So if I put this one here instead, I'm not sure if this is going to work here. There we go. 4.5 total, 1.5 in this one, 1.5 in this one, and then I think you can believe that's 1.5 in this one. And I showed that each one of these here has 6 volts across them, so each one of them gets 9 watts, which is the same as it was in the simple single bulb circuit earlier on, and a total of 27 watts. Okay, let's go back to the other part of the problem. So here it says, for a parallel circuit of 3 different resistors with resistances 330 ohms, 560 ohms, and 680 ohms, and a voltage source that provides 60 volts, compute the total resistance and the total power output. So the circuit is going to look as such. I think I need a little bit more space here. There's 1, 2, 3. Sorry that I counted, didn't have to do that, but here we go. So there's the ammeter. Maybe I'm talking to myself here so I won't forget anything. There we go. There. And there. And I guess drawing them vertically, I'm not that good at it. There we go. Alright, so this one is 330 ohms. I remember the last one, 680 ohms. And the one in the middle was 560 ohms. And this one over here is 60 volts. Okay, the same rules would apply. Each device connects to the same 2 points of the circuit, the voltage is therefore the same across each device. So actually that one we do know, 60 volts across each one of these. Okay, then the current divides among the parallel branches. Ohm's law applies separately to each branch. So each one of them is going to get some current. By the way, which one gets the most current? And you may have heard this before, the path of least resistance, and that indeed is this one here, the one with the 331 will end up with the largest current. And I'll show you in just a moment, because it says Ohm's law applies separately to each branch. So I1, the individual current for the first resistor, would be 60 volts divided by 330 ohms. And I do that separately here. I come up with 0.18 amps. Then the one in the middle, I2, equals voltage divided by the second resistance, 60 volts divided by 560 ohms. That looks like a little bit more than 0.1 amps. And I come up with 0.11 amps, rounded. And the third one is over R3, 60 volts divided by 680 ohms. So it looks a little bit less than 1 amp, and I come up with 0.09 amps rounded. So those are the three currents going through each of these resistors here, and they add up to the total current that flows through the circuit, where it says the total current in the circuit equals the sum of the currents in its parallel branches. So it's going to be that the total current, as written above for the other circuit, for the light bulb circuit, is I1 plus I2 plus I3 equals 0.18 amps, 0.11 amps, 0.09 amps, equals 0.38 amps, and that is rounded, so 0.38 plus or minus a little bit. So that's the total current. Well, that in turn will give me the total power for the entire circuit as total current times voltage, 0.38 amps times 60 volts, and again I do that on the side. That looks a little bit more than 20 watts, and I come up with 23 watts. That answers one of the questions. The total power dissipated is 23 watts. As far as the total resistance is concerned, so the equivalent or total resistance, that's the voltage divided by the total current. So that is going to be 60 volts divided by 0.38 amps. Look, somewhere around 150 or so. Let's see, I come up with 160 ohms. It's 157.89 ohms, but I rounded to 160 ohms because I only have two significant figures here. Okay, so this is the total or equivalent resistance, 160 ohms, which is in accordance to what it says about the resistance. As the number of parallel branches is increased, the overall resistance of the circuit is decreased. So as I add the 560 and the 680 to the 330, the overall resistance needs to be decreased from the initial one. And then overall resistance lowered with each added path. This means the overall resistance of the circuit is less than the resistance resistance of any of the branches, or in other words, the resistance, the equivalent resistance is less than the smallest resistance. So it has to be less than 330, and indeed I came up with 160. However, how do you put 330, 560, and 680 together in order to come up with 160? And for that, I'm just going to present that, how resistances are added in parallel, and that is as reciprocals. The equivalent resistance equals 1 over R1 plus 1 over R2 plus 1 over R3, and if we had more of them in parallel, then we would do that. Okay, now let's actually add them up. 1 over the equivalent resistance equals 1 over 330 ohms plus 1 over 560 ohms plus 1 over 680 ohms, and see what the calculator gives us. So let's see, move this over a little bit, and the calculator, it's good. Alright, let's see. 1 divided by 330 plus 1 divided by 560 plus 1 divided by 680. Hit enter, and I come up with this number here, 0.0063 rounded. 0063 rounded, but that's not the end result, because I still have to invert that, because it says 1 over the equivalent resistance equals this number here, and the units, by the way, at this point here are 1 over ohms. I need to have ohms as equivalent resistance. This is a typical mistake, stopping right here. This is not the equivalent resistance. If you get a number that is as small as this one here, almost ridiculously small, that is not the correct number. Instead, that needs to be inverted one more time, so 1 divided by that answer comes indeed out to the 159.0 that I had earlier on my calculator, or I calculated 157.9, but that's within rounding in between. Still, that rounds to 160 ohms as well, which is the same as calculated earlier using the rules for a parallel circuit and eventually coming up with the equivalent resistance. Let me just show you on a graphing calculator the way I usually do it. I open the parentheses, I type in my first resistance, and I know where the button is for to the -1, which is invert my number. Plus 560 plus 680, and then I close the parentheses, and now if I do that, I come up with that really small number, the 0.0063, but I know I need to invert it, so after I close the parentheses, I do again to a -1, which inverts it again, and that's why I put parentheses around this right away. So in parentheses, I invert each one of the numbers as I add them, and then after I close the parentheses, I invert it again, which then will give me this equivalent resistance, and when I hit the enter button, indeed I come up with the 159. Okay, let's look at the simulation. On this one here, I'm gonna remove the light bulbs. It always wants to hook up to this one here. There we go. Jeez. Oh yeah, I have to remove that light bulb there first. Alright. And actually, I will put yet another ammeter right there, and then I will put the resistances there. There we go. There we go. If we get readings right now, don't pay attention to them because I actually still need to change resistances and the voltage here. Whoa! Okay. That doesn't look good. My battery in flames. Oh no. Oh. Oh, that's a bummer. I didn't realize that. Did you just see that? In this applet, I can only go between 0 and 100 ohms. So I have to fake this here a little bit. You'll see in a moment. Let's see. Show value. Okay. Let's see. Oh, there we go. Show value. Show value. Show value. So what I did instead is I kicked each of the resistances down by a factor 10, and I kicked the voltage down by a factor 10. Notice that nevertheless the amps that I get, the total current is the same, 0.38 amps, and the way that it splits up is the same as we had calculated earlier as 0.18, 0.11, and 0.09 amps, and that is because I divide by a number that I divided by 10 and divide that by another number that was divided by 10. So actually for the currents that doesn't matter. And then for the total power I come up with 0.38 amps actually by our original 60 volts, which was I believe 27 or 23 watts. And then, oh yeah, as far as the voltmeter is concerned, yeah, we still get 6 volts across here respectively from the problem, actually 60 volts. And yeah, unfortunately it doesn't allow me more than 100 ohms here. That's why I had to kick these numbers down.